We now discuss the solution of a problem from the section Algebra that appeared in CSIR NET exam. The problem is on prime ideal and maximal ideals. This question has appeared in CSIR National Eligibility Test held on 26th November 2020. It is from the section C and it carries 4.75 marks. The problem is, let R and S be commutative rings with unity. Let F be a surjective ring homomorphism from R to S, and Q be a non-zero prime ideal of S. Which of the following statements are true? Options. 1. F inverse Q is a non-zero prime ideal in R. Option 2. F inverse Q is a maximal ideal in R if R is a PID. Option 3. F inverse Q is a maximal ideal in R if R is a finite commutative ring with unity. Option 4. F inverse Q is a maximal ideal in R if x power 5 is equal to x for all x belongs to R. We now discuss the solution of the problem. We have R and S are commutative rings with unity, and we have F is a surjective homomorphism from R to S, and we have Q a non-zero prime ideal of S. And let's take the statement that is given in option 1, that is F inverse Q is a non-zero prime ideal in R. We will discuss the validity of this statement. F inverse Q is an ideal of R because Q is an ideal of S and F from R to S is a homomorphism. By the definition of the prime ideal, Q is a prime ideal, Q not equal to S. By the definition of the prime ideal, Q not equal to S. And we are going to show F inverse Q is also a prime ideal. So F inverse Q should not be equal to R. So to show that, we first suppose that F inverse Q is equal to R. This implies F of R is equal to Q. R has a unit element 1. So F of 1 will belong to Q. But F of 1 is the unity element of S. So this implies F of 1 is equal to 1. This 1 is the unity element of S. 1 and F of 1 belongs to Q and 1 belongs to Q. That implies Q is equal to S, a contradiction because Q not equal to S. We are using the result if R is a commutative ring with a unit element 1, and U is an ideal of R, 1 belongs to U implies U is equal to R. So 1 belongs to Q, Q is an ideal. So Q is equal to S. We are using this result, a contradiction. This contradiction shows that F inverse Q is equal to R is not true. So therefore, F inverse Q is not equal to R. Given Q is a non-zero prime ideal, Q is non-zero, so therefore there exists at least one element in Q which is not 0. So there exists an element A belongs to Q, A not equal to 0 prime, where 0 prime is the 0 element of S. Since F is surjective and A belongs to Q in S and F is surjective, A has a pre-image in F inverse Q. So there exists an element that is pre-image. B is equal to F inverse A, which is also not equal to 0 in F inverse Q. This happens because F is surjective. So this shows F inverse Q is non-zero. Thus, we have proved Q is a non-zero prime ideal of S. Then we have shown F inverse Q is a non-zero ideal of R, and F inverse Q is not equal to R. It remains to prove that F inverse Q is a prime ideal, that we will show it in the next slide. We have the hypothesis. We have already shown Q is a non-zero prime ideal of S implies F inverse Q is a non-zero ideal of R, and F inverse Q is not equal to R. We will now show that F inverse Q is a prime ideal of R. For that, we will suppose that xy belongs to F inverse Q for xy belongs to R. We will show that either x belongs to F inverse Q or y belongs to F inverse Q. Xy belongs to F inverse Q implies f of xy belongs to Q. But f is a homomorphism. F of xy is equal to f of x into f of y, that belongs to Q, because f is a homomorphism. But Q is a prime ideal. So this will imply either f of x belongs to Q or f of y belongs to Q, because Q is a prime ideal. This implies either x belongs to F inverse Q or y belongs to F inverse Q. Thus, F inverse Q is a prime ideal of R. Xy belongs to F inverse Q implies either x belongs to F inverse Q or y belongs to F inverse Q, will imply F inverse Q is a prime ideal of R. Thus, if Q is a non-zero prime ideal of S, then F inverse Q is a non-zero prime ideal of R. This proves the statement given in the option 1. Therefore, the option 1 is true. Let's get into the option 2. The statement that is given in the option 2 is F inverse Q is a maximal ideal in R if R is a PID. So R is given to be a commutative ring with unity. Now we have to suppose R is a PID. In this context, F inverse Q, we have to prove that it is a maximal ideal. We have already seen F inverse Q is a non-zero prime ideal in R. Suppose that R is a PID. We recall a very well-known theorem that which states every non-zero prime ideal of a PID, principal ideal domain, is a maximal ideal. Here non-zero is an essential condition. Every non-zero prime ideal of a principal ideal domain is a maximal ideal, and it is a very well-known theorem. For those of you who want to see a proof of this theorem, please see Abstract Algebra by Dummett and Foote, and this is given in Proposition 7, page 280. So thus, suppose that R is a PID and every non-zero prime ideal of a PID is a maximal ideal. Therefore, F inverse Q is a maximal ideal in R. Thus, F inverse Q is a maximal ideal of R whenever R is a PID. This establishes the truth of the statement given in option 2. Therefore, the option 2 is true. Let's get into the statement that is given in option 3. Option 3 states F inverse Q is maximal ideal in R if R is a finite commutative ring with unity. R is already given. R is already a commutative ring with unity, the extra condition is R is finite. That we have to take into account. Let P is equal to F inverse Q. That is, P is a non-zero prime ideal in the domain ring R. Suppose that R is finite. Thus, we have R is a finite commutative ring with unity, and we have P is a non-zero prime ideal in R. And we can talk about its quotient ring R by P. So the quotient ring R by P is an integral domain. Why? P is a prime ideal if and only if R by P is an integral domain. Since R is finite, R by P is also finite. Thus, R by P is a finite integral domain. Therefore, R by P is a field. Why? Every finite integral domain is a field. Therefore, P is a maximal ideal in R. Here we are using M is a maximal ideal of R if and only if R by M is a field. So R by P is a field, which implies P is a maximal ideal in R using this result. Thus, Thus, P is equal to F inverse Q is a maximal ideal in R if R is a finite commutative ring with unity. This establishes the truth of the option 3. So the option 3 is true. We now go to the last option, that is option 4. F inverse Q is a maximal ideal in R if x power 5 is equal to x for all x belongs to R. We have already seen F inverse Q is a non-zero prime ideal in R. Let P is equal to F inverse Q, that is, P is a prime ideal of R, and we are given x power 5 is equal to x for all x belongs to R. Now consider the quotient ring R by P, and it is an integral domain. Why? Because P is a prime ideal if and only if R by P is an integral domain, and P is a prime ideal, therefore R by P is an integral domain. Let us take a non-zero element of R by P, that is A plus P, an additive left coset of P. Let A bar is equal to A plus P be a non-zero element of R by P where A belongs to R, and A bar is a non-zero element of R by P, therefore A belongs to R and A not equal to 0. By hypothesis, A power 5 is equal to A. Why? Because in R, x power 5 is equal to x for all x belongs to R, and A belongs to R. Therefore, by hypothesis, A power 5 is equal to A. Then A bar to the power 5 is equal to, A bar is A plus P to the power of 5 is equal to A power 5 plus P. And we know x plus p multiplied by y plus p is equal to xy plus p. Using that, a plus p to the power of 5 is equal to a power 5 plus p. A power 5 is a plus p is equal to a bar. A bar. So thus we have proved a bar to the power of 5 is equal to a bar, and it is in R by P, that is a bar to the power 5 minus a bar is equal to 0 bar. A bar multiplied by a bar to the power of 4 minus 1 bar is equal to 0 bar in R by P. This implies either a bar is equal to 0 bar or a bar to the power of 4 minus 1 bar is equal to 0 bar, since R by P is an integral domain and it has no zero divisors. That is why this happens. But we have a bar not equal to 0. Therefore, a bar power 4 minus 1 bar must be equal to 0 bar, and that will give you a bar to the power of 4 is equal to 1 bar. And now a bar to the power of 4 can be written as a bar multiplied by a bar cube is equal to 1 bar. And this implies a bar has a multiplicative inverse a bar cube in R by P. A bar is any non-zero element of R by P. Therefore, this shows that every non-zero element of R by P has a multiplicative inverse in R by P. Thereby, R by P becomes a field. Now, when R by P is a field, P is a maximal ideal, and we are using the result. M is a maximal ideal of R if and only if R by M is a field. Thus, we get M is a maximal ideal. So, therefore, P is equal to F inverse Q is a maximal ideal in R if x to the power of 5 is equal to x for all x belongs to R. So the statement given in option 4 is true. So the option 4 is true. So in all, our final answer is all the options, option 1, 2, 3, 4 are all true. That is our final answer, and that is the discussion of the problem on prime ideals and maximal ideals. I hope that you have understood the proof of the question that is given in the examination. I wish you all the best. Thank you.